well, I should say good afternoon, everyone. Well, I'm in the United States, so it's early morning here. Um, so I'm giving this talk on behalf of Dr. Scully, and because of recent COVID-19 surge here in local Texas, I mean he wasn't able to give his talk, so I'll give the talk instead in place of him. This work has been done, well, there are a series of works in this talk involving many of our colleagues, like Alexei Sokolov and Anatoly Svizinski. So, well, I might cough, so please bear with me due to the recent infection. So we'll be talking about a few topics that's been conducting. This research has been done in the recent decade. So all of these start with this one.
Laser experiments at Princeton University and Texas A&M could light the way to instant detection of anthrax spores in a letter or even in the wind. Researchers who reported their new technique in the journal Science believe it could be implemented in relatively low-cost detectors to monitor for bioterror attacks. Science and technology correspondent Patrick Regan reports.
In September and October of 2001, anthrax-laced letters postmarked Trenton, sorted in Hamilton, and evidently mailed from a box on Nassau Street in Princeton caused infections, 5 deaths, and disruptions of postal services, government activities, and commerce. That crime remains unsolved, but the problem of detecting anthrax in time to protect people may be closer to a solution. That's mainly because the anthrax attacks hit close to home for quantum physicist Marlon Scully, a professor at both Princeton and Texas A&M. In November 2001, a passenger reported finding white powder in her mail during a flight piloted by Scully's son, Jim.
It was just a scare. It wasn't a contamination, but obviously it would be nice to know right away and scientifically that it's not anthrax. And we had a lot of people who were in tears because they were scared.
At Jim's suggestion, Marlon picked up the challenge. After consulting experts at government and university labs, he set his sights on one particular molecule found in anthrax spores.
The bottom line is that this simple molecule is what we're looking for. And that molecule now we probe by using laser light.
Scully's Texas lab pioneered techniques for slowing the speed of light and, as he says, massaging molecules with it. His Princeton colleagues work with trains of light pulses as short as a few millionths of a nanosecond. Together, they worked out how to amplify what Scully calls the unique music of their target.
Think of the molecule as something which vibrates like a guitar string. And so we're probing that vibration with the laser radiation. We had to learn how to send in the preparation pulses that would start the molecule off with this motion and then that motion. There's 17 different ways that this thing can oscillate. And we had to pick 4 of them that were close together and get all 4 of those signatures at once. Now you can be sure, 99.99%, that it's not a false alarm and that you can pull the signal out from the background.
This technique has been developed, so-called faster course, which is the femtosecond adaptive spectroscopic technique for coherent anti-Stokes Raman scattering. It picks up signals from the anthrax spore via this molecule called dipyridinic acid, which basically is a pyridine molecule, and you knock off 2 hydrogen molecules and replace them with carboxyl group. And this molecule, by its weight, is about 17% in the dry sample. So that's the substance you can pick up with the optical technique. And in principle, well, and also as later demonstrated, I mean, this technique can pick up the signal with a single femtosecond pulse. So come back to Raman. I mean, spontaneous Raman has been discovered by Nobel Prize laureate Raman, but I mean the effect has been already theoretically predicted long before that was experimentally discovered by Schmeckel. So when a molecule vibrates and light scatter of that vibrating molecule, you'll be able to see, for example, two lines. One is called Stokes line, which the frequency is lower, and the other is anti-Stokes. The frequency becomes higher. And so here we talk a lot about coherence. In here, the Raman coherence, what we really mean is that the superposition of two vibrational levels. When you write down the wave function of the two state, the ground state is here, and the excited state is this one. And as you vary in the phase between the two wave function, you'll see that the internuclei distance will be changing, and that represents the oscillation of the molecule. And this is explained in quantum mechanical term. So when a photon scattered off a molecule, there are two processes. I mean, there can be many processes going on. The first one is incoherence, incoherent one. The pump photon is scattered off of a single molecule and generates Stokes photon. And there could be another process which many molecules are propelled in the coherent superposition state. And now when the photon hit those molecules, the coherent process will generate a coherent Raman scattering. And this can be described by an interaction Hamiltonian in this form. G is the Raman coupling constant. And this is the term describes the molecule, the generated signal photon, and the pump photon. And of course, the conjugate term describes the reverse process. After some simple calculation, you'll be able to find this term, which describes the incoherent contribution and the coherent contribution. The bottom line is the coherence term is much stronger than the incoherence term in the case that when the number of molecule is large enough and when the coherence is large enough. This coherence means the, let me go back one step, means the molecules are vibrating in unison. Many molecules vibrating in unison. That's called cooperative emission. So this has been verified experimentally at Princeton back like a decade ago, where you varying the power of pump and Stokes, which the coherence is proportional to pump and Stokes, as we can show in a PNAS paper. And here, this one, compared to previous equation, we have assumed rho cc to be 1. And this term describes the incoherence contribution. That's the collection efficiency. The omega is the solid angle of your collection device. So this contribution has been verified. And then all these technique has been applied to detect anthrax, and the result is reported in this science paper in 2007. And some take-home message from this technique, the faster cores first use a very narrow, broadband pump and Stokes, which in time domain are two short pulses, broadband, which can excite a large band of Raman vibrations, and then probe with a narrow band in frequency, and then long pulse in time domain, right after the excitation. And this skin can mitigate the unwanted Fourier mixing, because if you think of that, these pulses are all overlap. If you move this pulse ahead, overlap with them, you'll see a big non-resonant background. So as we pick up the fingerprint from the anthrax spore, you'll be able to identify the spore after a little bit time of integration. Instead of cultivating these bacterial and then trying to identify what they are. So a take-home message, and of course, over the years, we've been applying this technique to various problems. This isn't just some example on gas detection. Instead of having a broadband, a broad and hard to recognize coarse, typical coarse signal, and when you delay the probe to some to the north of the probe pulse, you'll be able to clean up the spectrum. This is on resonance, which is cut a slice from here, and the red one is a slice from here. So later we were able to show this technique can be used to detect gas distribution in real time. So coming next, are we able to use any of these Raman effects to do detection at distance? For example, a couple of 100 meters. So this work has been demonstrated back in 2014. So the basic idea is a Raman laser. So what is a Raman laser? A typical laser is that you put a game medium inside a cavity, and when the game can overcome the loss of the cavity, and laser oscillation will build up inside the cavity. And if you replace that game medium with a Raman media, well, you pump the Raman media and Raman photons being converted by the Raman media. And when the game is large enough to overcome the cavity loss, the Raman laser, Raman oscillation will build up inside the cavity. So this idea can be readily applied to a highly scattered media, through random walk. The cavity is now defined by the scattering, a closed loop scattering among some random particles. There is no need for cavity, but this process can be very efficient, up to a few percent of energy conversion efficiency from the pump. So this work has been demonstrated and then published in this PNAS paper. So there we're able to show that you can use this technique to detect white powders and distinguish them through their Raman signature at a couple of 100 meters. These are these white powders, and through Raman signature, we will be able to distinguish what they are, right, in their fingerprint region or the CH stretching region. And at distance, even at 400 meters away from this powder, and with a very cheap ocean optics spectrometer, we're able to distinguish different type of chemicals, white powders, these white powders, through their stimulated Raman signature. These are simulation results using Monte Carlo method. And later, in general, these scattering process has been also modeled to demonstrate spatially offset Raman spectroscopy to, for example, detecting bone density. So the basic process is that you send in the laser pulse, and depending on where you detect it, that's the offset. You put your probe here or here, the received signal will be different and is proportional, as shown from our simulation. It's proportional to the depth, the penetration depths. The further your offset is, the bigger depths you're detecting. This has been quite an effective tool to detect Raman signals at depth. So let me move on to the next topic. So these ideas have been extended trying to solve this problem of chemical sensing at distance. And some idea back 10 years ago was that if we can time somehow, if we can time some game at distance, for example, in this case, you send in some pulse train, and through dispersion, these pulses will be overlapping at distance at various time. And if you time them if you time them properly, then there'll be game generated at further distance, and then later game will be formed here and then here. And this game will be able to sweep the game, right, in the backward direction to generate directional coherent pulse in the backward direction. That means you're sending out a laser in the forward direction, and then you expect to see something in the backward direction. And this work, which Marlon is co-author, published in 2011, the same year, came back that, well, indeed, these game medium can be demonstrated, can be used even from the air. The basic idea is simple. We send in very strong UV pulse, nanosecond, picosecond pulse in UV range, and that pulse will be able to dissociate the oxygen molecule. And the dissociated molecule will have two components: an excited oxygen molecule and a ground state one. Well, then this ground state one will be further two photon excited to its excited state. And when it decays, this transition will provide enough gain to form a backward pulse. And our work later shows that, well, these signal in the backward direction and even further in forward direction are highly oscillating, in which case we were able to show theoretically and pinpoint that these processes are coherent process, which involves all these atoms that's been excited. They have inherent coherence that modifies the temporal distribution of the backward photon. So, okay. Last topic in our group is a new concept of quantum amplification by superradiant emission of radiation, which the acronym is Quasar, instead of well-known laser. This work was was first discovered by Anatoly Svizinski with colleague Lu Qiyuan and Marlan. The result was published in Physical Review X in 2013. And the idea went back to this time decay state. So basically, if you have a cloud of atoms and you send in photon, you send in for example, a laser pulse to excite them. So you don't exactly know which atom is excited. So you'll be able to time the phase between these atoms according to their position. And this was first proposed by Marlan, called time decay state. So one of the atoms are excited and with their respective phase. And so as you work out the problem, they were able to show that, well, it's very similar for the two different cases. One is that you have many photons in the cavity with a single atom, or another problem is you have a cloud of many atoms with a single photon. These two processes turns out to have the same dynamic. When you look at the excitation probability of the atoms, or collective excited probability. So now a question naturally come up. This process, which represent the stimulate emission process, which the interaction cross-section is proportional to the photon, square root of photon numbers. And in the other case, is proportional to square root of the atom density or atom numbers that's involved in this process. This process gives the foundation for laser, which is well-known stimulated process, right? And what does this term correspond to? Does it give us any new insight into a new kind of radiation? The answer is yes. And instead of a stimulated process, now you can coin a term called collective oscillation frequency, which we denote as omega A. And as you work out the Maxwell equation in slow varying envelope approximation, you get a working equation this way. Of course, the original Schrödinger equation, when you solve it directly in using the semi-classical way, these two terms, the coupling two terms, are for the wave, electric field, and the atoms are not symmetric. One is in first order, the other is second order. But after some good approximation, you'll be able to linearize these equations and obtain an oscillation equation. It turns out that these equations are well studied, actually. They're called Massieu equations. And if we were able to modulate this term, which is the population inversion term, right, from A to B, by an external drive at a small amplitude, this equation has some regime that provides gain to the propagation field. And the simulation result shows that in forward direction, there is no gain, but in backward direction, when your drive goes in one direction and a small laser pulse, propagate in the backward direction, well, this pulse should be on resonant with the atomic transition, while the drive is far off resonant, so that you can only drive a small population or small coherence between these two levels. The calculation shows that the input pulse will be enhanced enormously under some resonant conditions. So Marlan later revisited the problem and shows the striking symmetric structure of these propagation equations for the photon, and for the atom, as embedded in these two equations for dynamics of these two particles. And they share the same structure and shares the same gain mechanism. So take-home message. Well, this quasar is a new mechanism that utilizes the collective coherence of atoms or even molecular media to be able to amplify light wave. Of course, we've been continuously pushing this idea and see how we can demonstrate it in experiment. And it turns out that under under more strict simulation, it turns out that, I mean, if you turn on a long pulse, adiabatic pulse, turn on the pulse adiabatically, there won't be any gain. And if you turn on the dry pulse abruptly, that means very sharply, then the gain would show, indeed, the input pulse would show a strong gain after propagation. And the reason is that when you drive an atomic system for far off resonance, and if you turn on the pulse adiabatically, that means you turn on the pulse slowly. The population in the upper state will just follow the envelope of the pulse, of your dry pulse. But if you first create some create some coherence between these two levels, and then you turn on this adiabatic pulse to drive the system, then indeed you can show that Raman oscillations can be generated. And later this has been demonstrated experimentally with some effort, that when you send in an adiabatic pulse, indeed the envelope will follow the envelope of the dry pulse. But if you start with some initial coherence, then when you turn on an adiabatic pulse, we'll be able to see the Raman oscillation in the system. And this paves way for further, future demonstration of this quasar effect. So the goal at large is that if we can create some coherent beam in the backward direction, and then we'll be able to send in other pulses and to meet with the backward propagating emission, for example, a quasar pulse at distance, and generate coherent Raman beam, Raman signal in backward direction, so that we can detect chemical or other things at distance. And this ends my presentation, and hopefully I'm on time. Thank you very much. And I can take questions from you.
Thank you so much for your presentation. The floor is open for the questions. If from the on-site as well as from the online, any questions is there, you can ask. Dheeraj, can you have any question from on the floor?
Mm-hmm. You might need to repeat the question if there are any.
I am not getting any